about this question. Why do this figure skater or spin faster when they pull their arms in? Why? Actually, today we prepared, I asked the department for help. So I got those two devices. Okay, those are two heavy things. Maybe not that heavy. But let's see if I can do this without. So let me show you guys first. So we have this, right? Maybe in PE department you need to use to practice and gain your muscles. We don't want to get hurt, so maybe not this much weight. Let me see if I can slide it. But this, I don't know if this will be too light. This may be too light. I'll try this one first. Can somebody come here, give me a push? Okay. Also, can we have a cameraman to move the thing so that it can record this experiment? All right, so can you spin me? Try harder. All right. Okay. Maybe this is not heavy enough, so let me try to add some more weight, okay? All right, this is heavier. Okay, let's do this. Give me another push.
You get up.
Do I spin faster? Do I spin slower? Do I spin faster?
It's actually hard to spin.
Okay, I'm tired. Somebody else come here to this experiment. Who's strong? Make it strong? Alright, hold it. This one here, hold it. Alright. Sit. Alright. Extend, come back. Alright. Extend. Extend. See? Alright, so thank you so much. You can go back. Can you put it back here? Yeah, the top. Alright. Okay, so that's a little demonstration. Did you guys notice that when I spin Mingy, right, I asked Mingy to spread his arm, extend it to the furthermost, and then when I spin him like that, I give him an initial angular velocity, and then I ask him to pull back his arm. His angular velocity significantly increased. His spin is much, much faster. So that is something we're going to talk about today. Apparently, if you change the radius, it somehow changes your angular velocity, right? So there must be something, some relationship between the radius and the angular velocity here, right? The question is, what exactly is the relationship? So let's move on. First of all, there is a new concept that I need to introduce you guys, which is called moment of inertia, right? Moment of inertia. So we learned about the idea of inertia in MIT. Can anybody give me the definition of inertia? What is inertia?
Resistance to changes rotational motion.
Louder, please.
Resistance to its changing its original motion.
Okay, so an object's tendency or property to resist to the change of motion. And or we can say it is an object's property to maintain its original motion. But for inertia, it's mostly for the translational motion. Moment of inertia, on the other hand, it's also an inertia, right? So it is also a resistance to change of, but in this case, angular motion or angular speed. So let's consider a bowling ball on a tabletop like this, right? This is the top view, and right now it's stationary, so there's no kinetic energy, right? It's not spinning, it's not moving, completely stationary. And now if we rotate it, if we spin it, it's spinning in place, perhaps in ice. Now its EK is not zero because apparently it's moving, it's spinning, right? But we never learned anything of how to calculate the kinetic energy when something's spinning. We only learn when something displaces itself. Then we use EK equal to 1/2 mv squared to calculate the translational kinetic energy. So, but apparently we know that the kinetic energy could not be zero, right? Because you need to do work. You need to apply force, right? Or torque in this case to make it spin, right? Okay, so now, neither ball is rolling, but both balls have a translational kinetic energy equal to 0 because they're not moving translationally, right? Okay, and the second ball has only rotational kinetic energy, okay? So that's a new thing that we're going to learn today, rotational kinetic energy. What we have learned, EK equal to 1/2 mv squared, is by default we assume there's no rotation happening, right? So that's actually translational kinetic energy. So kinetic energy really depends, total kinetic energy really depends on two things. To see, one, if you're moving translationally, then you're going to use 1/2 mv squared to calculate. Two, if it's spinning. If it's spinning, then you need to add additional rotational kinetic energy. So far so good? Any questions? Okay? Okay. So, now, even though the center of the mass of the spinning bowling ball is not moving, each particle in the ball, not in the center, has a tangential velocity, thus has kinetic energy. So, it's the same thing as like Mr. Kai is spinning right now, right? But I'm not changing my direction. So, in the center, everything like here, 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 every particle here, down here, everything is stationary. But I spin myself, my hands here, they have velocity, right? Because you see, they are literally doing a circular motion here. So they have kinetic energy on those parts, not at the center. Everything else has kinetic energy. So in translation, every mass particle have the same velocity because if I move forward, every particle on me is moving together forward. We have the same velocity. But when you rotate like that, the furthermost have the greatest velocity. The closer to the center, the lesser the tangential velocity, right? Because tangential velocity equals to, if you still remember, V equal to radius times angular velocity, which is omega, right? Okay. So, now, that's not the case in rotation. Each mass will have a velocity that is proportional to its radius from the axis of rotation. So further away you are from the axis, the greater the velocity. Similarly, like here, if I have a meter rule, I hold this end and I rotate it like that. The velocity here is very small, right? But the velocity at this end is faster, right? Any questions? Okay. So in fact, if you recall for the circular motion we can see that it's actually here. This is our velocity, right? If this is how we calculate our kinetic energy, 1/2 mv squared. But the point is, each point on this bowling ball has a different velocity, right? So for each particle, we need to find its individual velocity. And we know that velocity equal to omega times r. Omega is the same for rotating object. Their angular velocity, because the time needed for all particles to complete one full circle is the same. So we can replace v with r times omega, right? And then you're going to get 1/2 mr squared times omega squared. Now, so we just need to find the particle here. Let's say if this particle, m1, actually this is m1, this is m2, this is m3. We just need to find m1 and then find its radius, which is r1, times its r1 squared, and then times angular velocity. That is the kinetic energy of m1, right? Because m1 has a velocity v1, and v1 equal to r times omega, r1 times omega, right? So we know that ek1 should be equal to 1/2 m1 v1 squared, which is 1/2 m1 r1 omega squared, which you're going to get 1/2 m1 r1 squared omega squared. If we decompose this bowling ball into infinity of particles, then we can use the similar steps. We calculate each particle's kinetic energy, and then we add them up together to get the total rotational kinetic energy of this bowling ball. Does that make sense? Okay, so we just need to keep going. Then, given that omega is the same for all particles in a rigid extended body, clearly the total kinetic energy is given by this equation. Ek rotational equal to 1/2 I omega squared, where I equal to the sum of all the particles' mass times its corresponding radius squared, which we call this moment of inertia or rotational inertia. Two names, same thing. Okay? Two names, same thing. So basically, what is moment of inertia? Moment of inertia is calculated by mass times radius. The radius is the mass particle, the distance between the mass particle to the rotational axis. Okay? To the rotational axis. And how do we understand it? Conceptually, just like how we understand the inertia in translational motion. Inertia is the resistance of change in motion, in linear motion. So moment of inertia or rotational inertia is thus the resistance of change in rotational motion, right? The greater the moment of inertia, is it easier or harder to spin it? Harder, right? Just like the greater the mass, it's harder to push, right? Harder to accelerate it. Okay, any questions so far? Okay, good. So, let's do, before this, let's correspond what we have learned in translational inertia. Just like we mentioned just now, right? We see that all the translational kinematics and dynamics equation can be directly translated into their rotational counterparts by simple substitution. One of which is I corresponding with M, right? This is the inertial mass. This is the moment of inertia. This, the greater the mass, the greater the resistance to change in linear motion. The greater the moment of inertia, the greater resistance to the change in rotational motion. Questions? Okay. All right, so let's do a practice. Find the moment of inertia of the dumbbell about its center. Each end has 15 kilograms. Assume that 30 centimeter handle is massless. I'm going to give you 2 minutes.
So whole handle is 30 centimeters.
Yes. Finish calculating. Mito, can you tell me how did you solve it?
Moment of inertia equals to sum of 3 specific equation times
15 squared.
But the one, is that 0.15
What do you think?
0.15?
0.15 squared? Okay, so it's rotating about this center, right? Right this point, right? And we assume that the 30 centimeter handle is massless, so all the mass is concentrated at those two dumbbell. Each one has 15. So here, 15 kg. Here, 15 kg. Radius is 0.15 meter. Here is also 0.15 meter. Right? So basically, moment in inertia, you just need to calculate each single one of them and then plus them together. So let's say I1 plus I2, which is M1R1 squared plus M2R2 squared. Now, because they're the same, of course, you can combine M1 and M2. Because radius is also the same, right? So we're going to get 30 times 0.15 squared. So the final answer is 0.675 kilogram meter squared. Questions? We all got it correct? Okay. Let's move on. Now, if the mass of the previous example is rotating once in 2 seconds, what is its rotational kinetic energy? Alright, this one, I'm going to walk you guys through it. Okay? So, first of all, what can we think of? Rotating once in 2 seconds, can we calculate its omega?
Yep.
So, omega equal to
2 pi over
2 pi, which is rotating once, that's the 2 pi is the displacement, angular displacement, 2 pi over 2 seconds. So angular velocity is pi rad per second. Okay? And we're looking for its rotational kinetic energy. as we just say that this is equal to 1 over 2. Jessica, what's the equation? 1 over 2.
I times.
Okay, so 1 over 2. I we just calculated from previous answer, which is 0.675 times pi squared. So we're going to get the rotational kinetic energy, which is 3.33 joule. Say 3.3 joules. We're okay? Any questions? Okay, so far so good. Alright. Don't forget, the unit is joule because it is kinetic energy. Right? It is kinetic energy. Now, if the mass of the previous example is not only rotating, but also translating, now what is its total kinetic energy? This one, I'm going to give you 2 minutes. You guys can discuss with each other.
What's the mass?
Mass 30.
on each side. So it's 30.
Mass 30. Yep, okay.
We already know the rotational kinetic energy from previous question is 3.3 joules. Now it's just on top of that, you're moving it translationally, right? So you just need to add an extra kinetic energy to it, right? Don't forget, total kinetic energy is equal to rotational kinetic energy plus translational kinetic energy. That's it. Nothing more.
What was the mass? Total
30.
Be quiet. I haven't asked the answer yet, right? And time is still there. Give time for each other. Give time for each other. Okay. Lindsay, do you have the answer?
4.27
That's the total energy? Okay, let's check answer. So previously we have 3.3. Now we just need to add translational kinetic energy, which is 0.94. So we just add them up together, which gives you 4.2. 啊，加法都能算错。Okay. Now, find the moment of inertia of the dumbbell about its one end. Each end has a mass of 50 kg. Assume that the 30 centimeter handle is still massless. Now we're not rotating above the center. We're not rotating like that. We're rotating like this now. So how are we going to find the moment of inertia now? 1 minute. You guys can discuss if you're not sure. 1.35 is correct. So basically, you do the same thing, right? You calculate the moment of inertia of each one. But since right now you're rotating about one center of this one, so this 15 kg, its radius is 0, right? Now this one, its radius is 0.3. So 15 times 0 squared plus 15 times 0.3 squared gives you 1.35. We're good? Okay. All right, so what did you notice? What did you notice? Karen?
Moment of inertia depends on the axis of rotation.
The moment of inertia depends on
Axis of rotation.
axis of rotation. Okay, so not just the radius, right? For example, again, like if I'm using this one here, to pull this thing up looks easier, but if you wanted to do it like this way, it's gonna be harder, right? It's gonna be harder. Or if you do this, it's easier. If you do this, it's more difficult. Okay. All right, so the practice question is similar. Let's jump. We don't have to look at this one. You guys can do this yourself when we're back. So here, as we have already know, that the moment of inertia depends on both the radius and the axis, right? So for example, if you pick the center as the axis, it's easier to rotate. But if you pick the end as the axis, it's more difficult to rotate. So the moment of inertia literally changes if you change the rotational axis. That's the reason why here we have given you the equations for calculating the moment of inertia for different shapes. And for a hoop, which means inside it's hollow, it only has masses at the edges. Then the moment of inertia is the easiest. It's mr squared. Mr squared. Why? Because all the particles have the same radius. Does that make sense? All the particles, all the small m, from m1 to mn, all of them have the same radius r. So moment of inertia is just mr squared. Now, for this one, if it's a disk or a cylinder, right, the moment of inertia becomes 1 over 2 mr squared. 1 over 2 mr squared. This, if you wanted to derive it, you can use calculus to do it. Alright. And then we have, if you, now see, those two, up and down, they're exactly the same shape, right? But this one, moment of inertia is mr squared. This one, moment of inertia is 1 over 2 mr squared now. What is the difference? So this one, how does it spin? It spins like this, right? What about the bottom one? It spins like this. Okay? If you spin like that, then all the mass particles about its rotating axis is the same radius r. But if you're rotating like that, then this here on the very top and this here on the very bottom, they have 0 radius. But here and here, further away from the rotational axis, have the largest radius r. Right? So each particle has a different radius. So you end up getting total moment moment of inertia about the diameter is 1/2 m1 squared. Similarly, if you rotate a disk across its diameter rather than its center, then we're going to get its moment of inertia equal to 1/4 m1 squared plus 1/12 ml squared. What is L? L is the thickness of the cylinder. Yes, you have
Do
questions?
we have to memorize all of them?
It will be provided during the exam. But if there is a law called parallel, we're going to talk about it later when it comes. But there is one thing that you should know. Okay, for solid sphere, moment of inertia equal to 2/5 mr squared. For spherical shell, which means inside is hollow, it only has the shell, right? If you cut it open, there's nothing inside, right? The moment of inertia is 2/3 mr squared. And for this one, angular cylinder ring, or it's a ring, which means it has an inner radius and an outer radius. Then the moment of inertia equal to 1/2 mr brackets, inner diameter squared plus outer diameter squared. Alright, even though some strange shape you don't have to remember, this one and this one, by default you have to remember about its center. By default you have to remember. Okay? Alright. Sphere, usually we wouldn't require you to think about, to know about this. Again, all of those moment of inertia equation you can derive yourself using calculus. Okay? Alright, so let's do one example. So find the moment of inertia of this 7.2 kilogram bowling ball about its center of mass. And a regulation ball has a diameter of 22. So let's go back. Now, it should be a solid sphere for bowling ball, right? It's not, is it hollow? I don't think it's hollow. Well, ignore that figure thing.
The mass distribution inside is different because there's different densities of
Different mass and substances.
Really? For bowling?
So the
Oh.
outside, inside is
For
different.
bowling masters.
Okay, how about let's just idealize it,
Okay.
right? Let's assume that it's a perfect sphere, solid sphere, then you're gonna use this I equal to 2/5 mr squared. Then, let's walk through this thing together. So first of all, we're gonna use the rotational inertia formula for a solid sphere, which is I equal to 2/5 mr squared. That you can calculate the moment of inertia, which gives you 0.035. And then since it's asking rotational kinetic energy, what is the formula for rotational kinetic energy? EK equal to 1/2 I omega squared. We already figured out I, so we just need to figure out omega next. Again, it's rotating twice revolve each second, right? So, which means its rotational speed is 4 pi rad per second, right? 4 pi rad per second. So 2 pi divided by 0.5, which is 4 pi. Now you can calculate its kinetic energy, rotational kinetic energy equal to 2.8. Alright, so, and we have rods, right? We have so many different shapes. For rods, if you rotate from this end, what does that mean? That means you're rotating like this. You're rotating like this from this end. Then the length is L. Its thin rod about the end equal to its moment of inertia equal to 1/3 ml squared. If you're rotating about the center, moment of inertia is much smaller. It's 1/12 ml squared. 1/12 ml squared. Okay. And then we have a slab. Slab about its center, then this is the formula for you. Okay, if we have this strange shape, usually we will provide the equation for you. Right? But regular shape, you should remember. Okay, so to sum up, we have all those here. This is frequently test, which means you need to remember. This is frequently test, which means you need to remember. Sphere, so far so good. This one you probably need to remember. This one you don't. Usually we don't test that much. Yeah, I would recommend you at least remember those three.
Oh, is the L the diameter?
What? L?
Yeah.
Length.
Length.
The whole length.
Yes. Any other questions? Okay. Make sure you also take down the axes because different axes causes a different moment of inertia. Okay? Even for the same shape. Okay, can we move on? Alright. We're not going to do this practice because it's just simply finding the values and plug it in. So let's look at the question here. Note that the moment of inertia about the end of the ruler is more than about its center. Why? Ayo? Vito. That's why I call you. Because the radius is much bigger. Okay. See, because the mass making up the ruler is on average further from the point in the former case. So for example, if you rotate it from the center, what you can do is you can divide this into two parts. And then what's the center of mass at this left-hand side? Here, right? What's the center of mass of the right-hand side? Here, right? So basically, you're concentrating all the mass here to this point. Concentrating all the mass here to this point. So then, this is, if the whole length is L, this is 1/4L. This is also 1/4L. So the moment of inertia is I equal to, if total mass is m, then this is m/2 times 1/4L squared plus another one, so times 2 before, right? But if you do it from the one other end, then you need to take the whole thing, which is the center of mass is here, right? This is L/2. And the center of mass, that's the total mass m. So the moment of inertia equals to m times L/2 squared, which you're going to get 1/4 mL squared. Here, if we do it, you're going to get 2 and 2 cancel out. So m times 16. So you're going to get 1/16 mL squared. See, if you pick on the end, the overall average distance, average mass distance from the pivot is further. So that ends up a higher moment of inertia. Okay? 5 minutes break. Anybody who's interested in to try the spinning thing? You're welcome. Okay. Let's keep moving. So, this is what I'm talking about. The parallel axe theorem. So, if you find in a situation where the shape is actually regular shape, like a rod or like a sphere, but the axis is so weird, like it does not pick the center or the diameter. It picks some point outside of it. Spinning it like that. Then how are you going to find the moment of inertia? Of course, the greater the radius, the more difficult to spin it, right? So the moment of inertia would also change. Right? So in this case, we will introduce you the parallel axe theorem so that for any position of the axis that you find, that you can figure out the moment of inertia. So for example, suppose instead of rotating the ruler about its end, for which we have already a formula, which is 1/3 ml squared, or its center, which is 1/12 ml squared. We wish to rotate it about a point 1/4 of a meter from the end, for which we don't have a formula, right? Where's my meter? Oh, put me in. So, right, you want to rotate it about a point 1/4 of meter from the end. Now, instead of having an infinite number of formulas for each extended mass shape, we have the parallax axis theorem presented without proof here, that the parallax theorem is IP equal to ICM plus MD squared. What is IP? What is ICM? What is MD squared? Well, so now you just need to know ICM. CM stands for center of mass, right? So that means the moment of inertia at any point that you find is going to equal to moment of inertia about its center of mass plus the mass of the object times. Now the d is the distance. The new parallel axis is from the center of mass axis. We're going to do an example, so to help you understand how to use this formula. So, for example, find the moment of inertia of a rod about its end if it has a solid sphere on the other end, right? So we're going to rotate it like this, right? According to this theorem, what we can do is we're going to find the center of mass, right? So let's walk you guys through step by step. Now, let's start with the formula for a thin rod about its end. Do you still remember? Okay, it's 1/3 ml squared. So we can calculate I rod is 256. Then, for the solid sphere, its center of mass is equal to 2/5 because it's solid sphere, right? And we're finding its center of mass first, which is 6 in this case. How far away is its center of mass to the new rotating axis in this case? 8 meter plus 1 meter diameter, so 9 meter away. So you're going to use the parallel axis theorem here. So the IP is equal to the ball, which is ICM, 6 here, plus MD squared. The mass of the ball, which is 15 kg, times the new diameter, which is 8 plus 1, 9 meters squared, gives you 1,221 kilogram meter squared. This IP is only for the sphere. So you're going to do is the total moment of inertia equal to this IP plus the rod. Together, you're going to get 1,500. Do I make it clear? So basically what you do is you separate this thing into two things first, right? Because this is a strange shape, but we know that this rod is a regular shape. This solid sphere is another regular shape. We can directly calculate the rod because we know the formula of rotating a rod about 1 n. That's 1/3 ml squared, right? And then, but we don't know about the formula of a sphere that is rotating about a point outside of its own, right? We only learn about its center of mass or axis. So what we're going to do is we're going to use this thing to decompose this. Let me use a different color. So for ball, I'll use blue. Then first of all, we're going to find the blue ball's its own center of mass about its center of mass. Its own moment of inertia about its center of mass And then we're going to calculate how far it is, considering it as we shrink it as a point mass. And then this point mass has a diameter of 9 meters from the rotating axis. So we're going to use ml squared or md squared to add this extra moment of inertia to the ball. And then don't forget, you need to add the rod back. So in total, it's going to be the rod plus the balls. And the ball has two parts, its own moment of inertia about center mass and the parallel part. Do I make it clear? This is the most confusing part. My previous students, a lot of them are very confused about this part because they forgot to add this md squared here. Okay? Questions? Alright.
This torture never ceases.
So we have a lot of equations.
Are you pondering what? Are you pondering?
Right? Actually, instead of directly giving you, I'm gonna give you the black one and ask you the red one. So what is the corresponding one for F equal to ma in rotational format? Torque equal to I times alpha. Basically, just replace each letter, finding its corresponding term in rotation form. What is corresponding to F? Torque. What is corresponding to mass? Moment of inertia. What is corresponding to acceleration? Angular acceleration. So, torque equal to I times alpha.
Are you pondering what I'm pondering?
What about this one? 1/2. What is corresponding with M? I. What is corresponding with E? Omega. So 1/2 I omega squared.
Are you pondering what I'm pondering?
I think so, name. But if you replace the P with an O, my name would be Oiki, wouldn't it?
Okay, so SUVAT, not T, SUVAM and F. Correspondingly, we have theta, omega, alpha, I, and torque. Alright, so let's do a practice example. So consider a disc-like pulley of a mass m and radius r. A strain is connected to a block of mass m, and wrap around the pulley, what is the acceleration of the block as it falls? This could be a little bit more challenging. I'm going to give you 5 minutes to discuss. Okay, don't work by yourself. Discuss with each other and find out how to do it. 5 minutes. Is it difficult? You got it? The answer?
So you get
Not sure? I don't know, I didn't calculate it. Okay. Alright. How about I'll do it together with you guys and you can check your steps while solving it. Okay? So, what do we know? Consider a disc-like pulley of mass m and radius r. So, since it has mass and radius r, can we ignore its moment of inertia? We cannot. So this pulley has moment of inertia. A strain is connected to a block of mass m and wrap around the pulley. What is the acceleration of the block as it falls? Is the acceleration of free fall? G?
No.
Why not?
Because
Is it free falling?
No.
What is the definition for free fall?
No other forces, only gravity.
The only forces acting on the object should be gravity. But apparently, if we do the free body diagram on this object M, it has, first of all, gravity, of course. Is that all?
Tension.
It also has tension from the strain. Is this tension from the strain going to be equal to the gravity?
No.
If it's equal, will it accelerate?
No.
So no, because it's asking for acceleration. In this case, the tension should be greater or smaller?
Small.
Smaller, because it's greater, it's going to go up, right? But it should be smaller in this case. It should fall down and accelerates downward. So we know that, okay. One thing about tension in a string is that the tension in a string at any point is equal in magnitude. So if here the tension give the strain give this big M, capital big M, a tension of T, then how much force the strain is exerted on this pulley small m?
Also T.
Also T, right? Because action reaction, right? Or in this case for the tension itself within the strain, that's an internal force that can cancel out. Okay, so then if we do a free body diagram on the pulley, what does the pulley have on the force? So first of all, of course, it has the weight, right? What else?
Sonic moment.
Normal
Normal
force.
force provided by
The
the hanger acting on
Pulley.
acting on which part of the pulley?
Center.
The center. And this should be
Balance.
balanced, equal, right? Is that all?
Line tension.
Where can I draw the tension?
At this side.
Can I draw it here? Why not? I just put all the forces at the center of mass.
Because the string.
Can we put the tension at the center of mass here?
No.
The strain is pulling the pulley at the side, right? So we cannot. The tension should be here. Does that make sense? Because if I draw it, this is the tension here. The strain is here, so the tension should be here. Is there any other forces? Or that's all?
That's all.
Okay, that's all. All right. So we do the free body diagram. All right. Now let's look at this. What is the acceleration of the block as it falls? So we have two objects here, right? And a string able to extend or contract. So whatever, like, if this object go down for 1 meter, then the strain should also extend for 1 meter. That means for this point, it should rotate for 1 meter. Does that make sense? Okay. So these two things is definitely somehow connected. Okay? Alright, let me erase those. Okay, let's focus on one object first. Let's look at the M. So we already know that it has weight and it has tension. That's all. So we're going to figure out acceleration. What equation should we use? For M, we're going equal to F net equal to MA. Oh. Why do I make it capitalized? Because we're only focusing on this object first, right? What's the net force acting on this big M? So that's everything we know for capital M, right? Okay, for small m, what do we know? We know it has W, it has N, all cancel out. The only thing is this T. What does this T do to the pulley?
Pulse.
It pulls so that the pulley
Spin.
spin. Will pulley spin at a constant angular velocity? No. Because net torque is not zero, so that it must accelerate, right? Okay, wait a minute. Then isn't it just another Newton's second law but in rotational format? So we already write F equal to MA. In rotational format, what should we do? Torque equal to I times alpha. Okay, this torque is produced by tension. So this torque should literally equal to, how do we calculate this torque? Tension times what? This torque equal to tension times r radius, right? Moment inertia, how much? Right now this pulley is rotating about, what's the axis of rotation?
Middle.
In the middle, okay? So for a disk, what's the formula?
Half mr squared.
Half mr squared. We should use small r. What about alpha?
Just like alpha.
Is alpha related to the acceleration here?
Alpha r equals to 8.
What's the relationship between alpha and the acceleration here? Is alpha the same as the acceleration here?
No.
This acceleration is a. Is alpha a?
No.
What's the relationship between alpha and a?
Alpha times r equals
So alpha equals
8. A over r.
a over r.
Remove all the r's.
So what do we know? What are the knowns? The knowns are small m, r, capital M. What are the unknowns?
A.
Unknowns are
A and
A and
T.
T. Okay, so we have one unknown, two unknown. We know this, we know this, we know this. T here the same, one unknown. The second unknown, we know R. Do we know R? Yes, we know R. We know small m, we know two unknown, two equations. Can we solve it? We can solve it. So to erase all those scratch, let's write down the two most important formula here using the red pen. So the first one is Newton's second law for translation of motion. We're going to get mg minus t equal to m times a. That's for capital M. For small m, we're going to get tension times radius r equals to 1 over 2 small m r squared times alpha over r. Let's erase all other things to make it clear. Where? Oh, yeah, good catch. A over R. Okay, so we're gonna solve it. Let's solve for t first. So t is gonna equal to what? According to the first equation. Mg minus a, right? And then we plug in t to the second equation. So capital M g minus a times r, because this in total is t, right? Times r should equal to 1 over 2 small m capital R squared times a over r. Let's do some cancel. So we cancel this r here. This r here also cancel out, right? So what we end up is capital M g minus a equal to 1 over 2 m times a. We open the bracket, so mg minus ma equal to 1 over 2 ma. We move this term to the other side, plus capital A. We take A out, we're going to get 1 over 2 small m plus capital M brackets A equals to capital MG. So we can finally get A. We just need to divide by this term. So finally we get A equals to mg divided by 1 over 2 small m plus big M. That's the acceleration. So if you take down step by step, you will notice that it's actually not that difficult. All you need to do is just to, step 1, do forces analysis, right? Draw free body diagram for each of the objects. Step 2, this M is doing translational motion, so use translational equation F equal to ma. Pulley is rotating, so we'll apply rotational equation. Use the rotational format of F equal to ma. Newton's second law, apply it twice. Once in translational form, once in rotational form. And then we have two equations, two unknowns. We just need to solve it to get. We can even get t. Since t equal to capital N, g minus a. We just need to plug this a back to this to get t, right? Simple math. The difficult part is to peel down the surface, right? 一层一层把它剥开，对吧？ Questions? We're good? Okay. All right. So final answer is here, like we just calculated, A equal to mg over capital M plus small m over 2. So did you get it correct? It's okay. Anybody got it correct?
If I simplify.
Almost. It's okay, it's your first time, right? It's your first time. Next time you can get it correct. Alright. So, rolling motion. Alright. A special subset of dynamic is called rolling motion, where by rolling we mean rolling without slipping. So that means, for example, this is what we call rolling. But is this also rolling? This is sliding, right? If it's rolling, sometimes it can roll and slide at the same time. Sometimes, okay? I cannot create this right now.
老师，你反光一下，你反过来这。
Yeah. That's rolling and the sliding at the same time. Okay. This is pure rolling. So the distance that it traveled equal to this here. Does that make sense? Do I need to prove it? Good. Alright. The speed of the wheel is given by VCM. Again, what is CM stand for? Center of mass. The center of mass, the velocity of the center of mass equal to S divided by T. Because the center of mass has moved horizontally from here to here. This displacement is S. Does that make sense? Okay. And the speed of the point on the circumference is the tangential speed. It's also given by this. Why? Because this particle has moved from here to here. The distance is also s, right? So the tangential speed, which is the speed of this particle, equal to the distance that it has traveled, which is this s divided by t. So same. Okay. Now let's consider this situation. Since Vt equal to R omega equal to Vcm, then we can write this. Vcm equal to R times omega. Condition for rolling motion. Take notes. So whenever it says something is rolling, this must be true. The velocity of the center of mass must equal to R times omega in order for it to purely rolling. Okay, move on. This only holds true for rolling without slipping. So pure rolling, pure rolling. All right, let's look at those scenarios. This scenarios, and here. If all those points are equal to the center of mass. Is it rolling? What is actually happening here? It's sliding, right? It's moving like this. So that velocity here equal to velocity here equal to velocity in the center. Now, for this one, here, what's the velocity at here? What's the velocity at here? What's the velocity here? And the center of mass is 0. In this case, what motion is it?
Rotation.
It's pure rotation, right? It's rotating. It's rotating like this. So there's no velocity at the center, right? The bottom, the velocity is going that way. The top, the velocity is going this way. Now, what is rolling then? This is rotating. This is translating. Rolling, at this point, what should be the velocity? That contact with the rolling. Velocity 0. Why? If you're rotating,
Oh, both sides better.
this is going that way, this is going this way. But if you're rolling, the point contact with the ground at here, how can I make it clear for you? If you at this point, right, you're rolling, you can think of this as doing this, right? The further away from this rolling point, this contacting surface point, the greater the velocity. This point, right, contacting with the surface is acting like a axis. Since it's right at the axis, there's no radius, right? So just like when you rotate, you can tell this end has a much larger velocity. As you go in, the velocity is decreasing, right? Right until you go to this point. Right until you go to this point, velocity will decrease to 0 because this point is right contacting with the surface. There's no radius, right? Okay. So here is 0. What about the velocity here? First of all, in which direction? This direction. Second of all, what's the magnitude? R omega. What about this point here? 2r omega. So if you can draw a velocity diagram, you can see the further away from the point, greater the velocity. The closer to this point, the smaller velocity. Why? Because at this position, at this moment, just think about this moment before and after. It rotates like this. If you think of it, if you take this as a stripes, if you cut this as stripes like this, right? Stripes like that. Then we only focus on the diameter stripe. It's rotating this way. Does that make sense? But here, it's rotating this way. That's the reason why here has the velocity going this way. Does it make sense? And here, it's moving this, like that. So this point, and the center point has the same velocity. This is very confusing, I know. I'm trying my best to make it visualize for you. Questions? Okay. Alright, so the rolling motion, we already have the parallel axiom, which you already know. And for any rolling objects, we have the total KE. Now in A4, whenever you're calculating kinetic energy, always think about, is there rotational kinetic energy, right? As long as it's rotating, you need to plus them together. Okay, so example, a 30 centimeter radius spool is rolling without slipping at a speed of 25 meters per second. What are the linear speed on the top, the middle of the wheel, and the bottom of the wheel? Yeah? Rolling without slipping. So what's the velocity at the bottom? 0. Okay. Velocity in the middle should equal to r omega.
Which is just
R equal to 0.13 meter. Do we know omega? At the speed of this,
just
It's 25 over.
just speed.
这个是不是就是 the speed of the center of mass?
Yes.
对吧? So it's equal to 25 meter per second. Then what about on the top? Double it, right? Just double it. So 50, 25, 0. Questions? Okay. All right. Okay. A4 question book. Did you still have it with you? Let's do a question from A4 question book. Let's just work on question 2. 来等一下。Actually, work on question 3. Okay, I'll give you how many minutes? Let me see. Oh, 没有 minutes.
没有 ，question 3也不是，是 KE，老师是 KE 的。
OK， 没有时间了，那我们就今天先休息一下，好吧？就不上完了。
嗯